This is a video about refraction. One of the things we need to know about different light media, in other words, things that light travels through like air and glass and water, is this thing called the index of refraction. All those different materials have different indexes or indices of refraction. They're calculated by taking the speed of light, which is a constant, in a vacuum, 3 times 10 to the 8th meters per second, and dividing it by the speed of light through that particular medium. So for example, the speed of light in water is, the speed of light in water we can calculate by using the fact that the index of refraction in water is 1.33. So we would take this equation, rewrite it so it's solved for velocity in that medium, take the speed of light in a vacuum and divide it by this index of refraction, and we'd find out that the speed of light in water is 2.25 times 10 to the 8th meters per second. Okay, so as we've learned, light bends when it goes from one medium to another. It bends according to Snell's law, which is this equation here. It says take the index of refraction of what material you're in, so in air, multiply that times the sine of the angle of your incident ray relative to the normal line. That should equal the index of refraction of the medium you're going into times the sine of the refracted ray relative to the normal line. So to answer this question, light is incident upon water at 25 degrees. What is the refracted angle? What is the reflected angle? And what is the refracted angle? The reflected angle we already know would be 25 degrees because there would be a ray of light that bounces off right there. But that's not what we're interested in right now. We're more interested in the refracted angle. So we would take Snell's law and solve it for theta 2. That's our unknown. We know theta 1 is 25 degrees. We know the index refraction of air that we're coming from is 1.00, and the index refraction of water that we're going into is 1.33. So we rewrite this equation for theta 2. It algebraically becomes this expression here. We plug in n1 as being 1.00. We take the sine of 25, make sure you're in degree mode in your calculator. We divided that by 1.33. We take the inverse of what's in the parentheses, and we get an angle of 18.5 degrees. So this ray of light bends toward the normal line like we would expect, because it's going from an index of refraction that's lower to one that's higher. It was 25 degrees between here and here, and we're going to find out that it refracts 18.5 degrees when it goes through the second medium. All right, now I want you to list what the conditions are for refracted rays. Do they bend away or toward a normal line? And what are those conditions? When does the ray bend away? When does the ray bend toward? All right, so for now, we're going to skip optics through a slab. One of the things you should just know, I'll tell you really quickly, is when you go through a slab, that's a series of these rectangular optical medium. It's always going to come out here as being the same angle. So it's going to come out here 75 degrees. We may or may not come back to that. All right, critical angle and total internal reflection. Let's look at this ray of light. This ray of light goes from glass to air. When it bends away from the normal line. As this angle increases, as this incident angle increases, the refracted angle bends further and further away to the normal line until there's this really special angle called the critical angle. That's when the angle bends at 90 degrees relative to this normal line when it's refracting. Anything greater than that angle will totally internally reflect. That means all of the rays will bounce back, none will refract out. Okay, so let's figure out what the equation is for total internal reflection. So first of all, theta 1 over here, we're going to make this critical angle. So we're going to focus on this red ray, right there, we're going to make theta 1 the critical angle. The sine of theta 2, that's from here to the normal line, that's the angle that's refracted out, that's 90 degrees. So from there to there is 90 degrees. We know that the sine of 90 is 1. So if we substitute into that equation, we'll get n1 sine theta critical is equal to n2, because again, sine theta 2 just became 1. Then we end up with this equation here if we divide both sides by n1. So the equation for critical angle is that the sine of the critical angle is equal to the ratio of n2 over n1. A mnemonic that might help you remember this is that n2 is what the light is going into. So right here, n2 is what the light is going into. So that's a little mnemonic to help you remember that. Okay, so for example, what is the critical angle for light leaving a swimming pool? So this is an example of it. Again, we'll just focus on that red ray. N1, what we're coming from, is 1.5. What we're going into, N2, is 1.0. Let's plug that into this equation there. So the sine of the critical angle is 1.0. That's what we're coming from. I'm sorry, that's what we're going into. That's on top, N2 is on top, 1.0. 1.5 is where we're coming from. If we take the inverse sine of both sides, we find that it's 42 degrees. So this angle here is 42 degrees. Any ray of light going into this boundary greater than 42 degrees is going to totally internally reflect. None of it will refract out. All right. What are the conditions for total internal reflection? The conditions are the ray must be exiting a region of higher index and entering a region of lower index, and the angle of incidence must be greater than the critical angle. So this example is one in which we're going to look to see what happens to the reflected and refracted rays until the light exits the slab. So we got this ray coming in at 30 degrees. Outside is air, index of refraction is 1. The glass on the inside has index of refraction of 1.50. So here comes that ray of light at 30 degrees. And we know that some of it is going to reflect, a very small percentage is going to reflect, again at 30 degrees. Then we're going to use Snell's law. We're going to solve Snell's law to find out what angle is the angle of refraction. We're finding out that it's 19.47 if we use Snell's law. So it's refracting, it's bending towards the normal line because it was 30 and now it's 19.47 degrees. All right, so now we got to do some geometry because this ray of light bounces, it goes in a straight line and hits there. This makes a right triangle where this is 90 degrees. That, as we calculate, is 19.47 degrees. And so that angle there must be 70.53 if the whole thing is going to add up to 180. All right, now, if we use Snell's law for this location here, we'll find that it doesn't work. The calculator will give us an error. And here's the reason for it. It's beyond, it turns out that this is greater than the critical angle. So whenever we're in a ray, in a object of a high index of refraction, we're trying to go to a lower index of refraction, we should always calculate out what the critical angle is. So let's calculate out this critical angle. Remember, N2 is what we're trying to go into. We're trying to go into air, so that's 1.0. We're coming from the glass, which is 1.5, and we're finding that we're getting an index of refraction of 42, a critical angle of 42 degrees. Well, our angle there of 70.53 is greater than this 42 degrees. So that means we're not going to get any refraction. We're instead going to get total internal reflection. So this ray of light will reflect instead of refracting. All right. Now, to figure out what happens next, we got to do some more geometry. If we look at this 70.53 degrees, again, that's 90. This turns out to be 19.47 degrees, which is pretty convenient because it was the same angle as over here. And if we kind of work backwards, we'll find that the angle it will exit at is 30 degrees, which is the same angle that it came in as. All right, and finally, we'll also get some reflection. Okay. And the reason for that is that we are less than the critical angle at that point. Now, it told us to stop when it exits the slab, so we're going to stop there. Now, finally, one thing that you need to know is that different frequencies of light have different indices of refraction. So if white light, which has all the different types of light, all the different frequencies of light, all the different wavelengths of light, hit a glass prism, they will bend differently, okay? And the reason for that is different indices of light have different indices of refraction. The reason for that is that different frequencies of light have different wave speeds within the medium. So this V is going to be different for all these different wavelengths or frequencies of light. Therefore, their indices of refraction N is going to be different as well.